Okay, so what we're going to go over today is something that ties in what we did last class with what we're going to be doing next class. So next class we're going to go over something called nuclear equations. In order to be able to write nuclear equations, we have to know these different symbols. And then have an idea of why do we do these types of decay is our other goal for today. So for alpha decay, there's actually two different symbols I want you to write down when we're talking about alpha decay. The first one is kind of a cursive A with a 4 and a 2. The second one is actually the symbol for helium. What we are going over right now is if a nucleus is unstable, how does it get to become stable? That's the kind of goal of our lesson today. When I show you the alpha symbols, either A for alpha with a 4-2, or what we usually use is 4-2-HE, if an atom loses part of its nucleus because it's unstable, it could lose an entire alpha particle. An alpha particle is essentially a helium nucleus. It has a mass of 4, that's why the top number is 4, and within there it has 2 protons as well. So when I say change in mass, the mass is going to go down by 4. It's losing a pretty significant chunk out of itself. But sometimes if you're really unstable, you've got to do that. Since this bottom number is a 2, that means there's 2 protons, so it's going to, the atomic number is going to go down by 2. After all, the protons, the atomic number, is the identity of an element. If the protons change, you have a new element. And the mass has changed as well in this one. The mass has gone down by 4. Last thing to bring up on this one, when does it occur? When elements are too big. Uranium-238. Let's start a class. We went over the fact that the proton-neutron ratio isn't that bad. However, it's bigger than lead on the periodic table. It is too big. A nucleus can only withstand so much repulsion. It can only be fit into such a space. And when it's too big, it is unstable. Uranium-238 is something that would go through alpha decay. I mean, think about it. If you are losing something the size of a helium nucleus, you're probably pretty big to start with. To be able to lose a chunk of your nucleus. Okay, nucleus just is kind of unstable. Kind of think of this idea of shaking, trying to hold it all together, but it's difficult to hold it all together, and all of a sudden something just pops out. It's ejected. It's emitted. After all, alpha decay is a very common thing. Don't know if we've heard in the news, I read this, I think, just recently, that there are some, like, grocery stores and things like that are no longer going to sell helium balloons, or they can't right now, because there's a helium shortage. There's only one place that we can make helium, alpha decay. Now, when that alpha particle is emitted, that does not include electrons, but usually electrons can then be attracted to that positive helium nucleus that's being emitted. You remember the gold foil experiment from first semester. Ernest Rutherford shot alpha particles at gold foil. Well, all he had was something radioactive, and he was able to then point the beam that radioactive decay was going to be shooting towards that gold foil. So big elements try to get stable. One of the ways is through alpha decay. the more or less loss of a helium nucleus. And what we're going to be going over next time is this can happen multiple times as well. Sometimes one decay is not enough to get you fixed. All right, beta decay is next. Again, beta was one of those old symbols as well, so there's a couple symbols for that. One is kind of this cursive B with a 0 minus 1. The other one the video kind of alluded to, the lowercase e. Notice the top number in either of these symbols is a 0, which means change in mass. The mass is going to stay the same. Now, beta a little unusual. If you look at alpha, change in atomic number went down by 2. What do you think the change for beta for atomic number is going to be? Up by 1. Which if you change the atomic number, it's a new element. But it'll have the same mass. Beta decay is to solve the issue of too many neutrons. Again, I know that neutrons supply the strong force and don't have any repulsion, so we think of them as a good thing. However, that band of stability graph reminds us of it's a ratio of protons to neutrons. There is such a thing as too much of a good thing. Again, if I go back to the previous slide, that hydrogen example had 1 proton and 2 neutrons. It had too many neutrons. So beta decay is going to try to solve that problem. Now, it's a little confusing. So what I'm going to do is use a bowling ball to explain this. Here's a bowling ball. We're going to think of it as a proton. Here's a little wooden sphere. We're going to think of that as an electron. You know, they kind of orbit around. Proton's a positive charge, electron's a negative charge. Remember, beta decay, just as the video showed, kind of talks of beta being similar to an electron. Although electrons are not in the nucleus. Electrons are orbiting the nucleus. So why do they call it an electron? If you take a proton with a positive charge and an electron with a negative charge, and you put the two together, you get a neutral charge. And as a matter of fact, the mass of a neutron is slightly bigger than the mass of a proton. And that slight difference is pretty close to the mass of an electron. So we can sometimes think of a neutron as a combination of proton and electron. If a nucleus has too many neutrons, it is unstable. Again, I try to shape to show you that idea of we're trying to hold something that's unstable together. And if it's unstable, something could just shoot out. And if I take a neutron, which again is the ball with the wooden sphere, and then it loses the wooden sphere, I've turned my neutron into a, what's left over now? Proton. That's the easiest way to explain beta decay. That's why that video talked about the fact that beta is like a stream of electrons. Because in essence, why we use a lowercase e, which is the symbol for an electron, in essence, a neutron is like a proton and electron combined. Now we know the quark theory says it's more about up and down quarks that make these things. However, the best explanation for beta decay out there is dealing with that idea of a neutron is a proton with an electron, and it loses the electron part. And if you lose your negative, you become more positive. So beta decay occurs when a neutron turns into a proton. If you gain a proton, your atomic number goes up by 1. Trying to achieve a better ratio between these two things. I'll give you another example of beta decay. If you've ever heard of something called carbon dating, you know, you have a fossil. How old is this fossil? Oh, we found a wooden bowl that, you know, years ago they might have used as a tool or whatever it might be. Carbon dating is dealing with that. The most common isotope of carbon is carbon-12. Even number of protons and neutrons, 6 of each. Carbon-14, on the other hand, has 6 protons, because it's carbon, and 8 neutrons. Not an even balance. This top one here is the unstable isotope. Again, it has 6 protons and 8 neutrons. What beta decay does then is that unstable nucleus is going to break down over time. Now, nuclear decay, we know how long it takes. That's a topic called half-life that we'll cover at the end of this week. But we know one of those neutrons is going to turn into a proton, which now would leave us with 7 protons and 7 neutrons. What element is element number 7? Nitrogen. 7 plus 7 is 14. Through that type of decay, we now have a more stable isotope. Even number of protons and neutrons, it makes nitrogen. In essence, whatever carbon-14 was in that fossil now becomes nitrogen in the air. And what they're able to do is we know percentage-wise within carbon, just a sample of carbon, how much of it's carbon-12, how much of it's carbon-14. As living beings, you are constantly consuming things that have carbon in it to keep you going. But the second you die, you are no longer replenishing your stock of carbon-14 along with the carbon-12. The carbon-12 is going to stay though, because it's stable. But that carbon-14 can break down over time. It takes thousands of years. So it's not like we use carbon dating to tell how old a cat that died 10 years ago when it actually died. I mean, this is used for old things. But we know that rate of decay, and we know by measuring how much is still in it of carbon-14, they can do a little backwards math to figure out how old is that fossil. So beta decay, not only is it used to keep things stable, but it's also used in other applications as well. Next, positron emission only has one symbol. 0 plus 1 in E. Once again, there's a 0 on the top for the mass number, why we had to remind you of these standard model, how to write down your isotopes. Positron emission. It's going to make that atomic number go down by 1. Which means, once again, we have a new element. At the same mass. Positron emission solves the problem of too many protons. I go back to our startup, the oxygen 15 had 8 protons and 7 neutrons. More protons than neutrons is not a good thing. So we need to change that. Now, unfortunately, protons just don't get lost. The nucleus itself doesn't just get rid of an entire proton. So it has to go through positron emission instead. And just like when I showed you here a minute ago, how in beta decay, a neutron turned into a proton, the exact opposite happens with positron emission. Now, positron emission, the explanation really has to get more into the quarks, of flipping a quark from a up quark to a down quark type stuff. So we don't get into the mechanism of how that works, although positron, positive, needs to be lost. We got to get rid of one of those protons somehow. And again, elements just don't emit a proton. I gave you an example of carbon dating, how beta decay is a very common one. For positron emission, if you've ever had a PET scan, a PET, PET is positron emission topography. So they are using that type of radiation as a way to detect something that's wrong within the human body. I mean, radioactivity is actually used a fair amount within diagnostic medicine. I know my brother had a thyroid condition years ago, and he had to drink a radioactive dye. And over time, it's going to decay. And then they start to take scans then of how is his body using this up, or where is it going to. So we've used it for medicines as well. Radiation therapy is dealing with that as well, of giving someone, again, cancer is one option, but it could be other things as well, that is going to give off these harmful rays, trying to kill the cancer within. The video that you saw a little while ago showed the fact that some rays can only penetrate through the skin. Some can penetrate through further and further. But if you ingest some of these things, they are in direct contact with what they need to be possibly setting radioactivity into. So positron, again, solving that problem of too many protons. The last one is gamma decay. Typically, gamma decay symbol doesn't even have numbers on the side because there is no change to mass. There is no change to atomic number. Gamma is energy that's released. So not only during decay could you lose an alpha, could you lose a beta, could you lose a gamma. But gamma is brought up, as one of the points I had on the board at the start of class, in relation to the conservation of mass law. I'm sorry, energy law. My fault. So in all three of these unstable ones, the hydrogen, the oxygen, the uranium, not only will hydrogen, because it has too many neutrons, go through a beta decay, oxygen, too many protons, go through positron emission, uranium, too big, go through alpha decay. Not only will they do that, but they will also go through gamma. The best way to explain gamma is to remember that if a nucleus is unstable, it takes a lot of energy to hold it together. Now, if a particle is lost, and that nucleus is now a little bit more stable, the atom has extra energy that it no longer needs. That energy is also released. So that radioactivity that's often brought up in movies, that radiation that's coming off, that energy that, again, can cause people to get ill. You see them in movies that their skin gets bad or whatever it might be right away if they're exposed to it. That is the energy from the gamma decay. That when you have high energy holding a nucleus together, and now a nucleus is a little bit more stable because it's gone through decay, it releases that energy. energy is conserved. It came from somewhere. If you guys were not a good class, it would take a lot of energy for me just to keep you from tearing each other's heads off. Now, I'll give you an example from prior to my days here. When I substitute taught years ago, I substitute taught in, I think, a 6th grade class in Verona. And I was the 3rd sub in 3 days, which is not a good sign, because usually you want to get the same sub back, but as a sub you could say, I don't want to come back. And that's what I said at the end of this particular day. And the class was just unruly. They could not control themselves at all. And at one point, these 2 girls were kind of play fighting a little bit in the middle of the room. I don't know why. And one girl punched the other girl in the shoulder. The other, again, this is between 4th and 6th grade. I'm not exactly certain what grade it was, but it was below middle school. The other girl's response was to yell out the F word as loud as she could. You can't really let that slide. Whether you are middle school, elementary, high school, it doesn't matter. You say that word, bells should be going off of. No. Society says that you're not supposed to be just yelling this out in any circumstance. So I had to send her to the office at that point. Now, on her way out, she also decided to get me one more time because it's my fault that she said that. She said, I hope you die. And, yeah, she hoped I die and went to, well, not heaven, but somewhere else. And then as she slammed the door on the way out, she said, why do you have to be a little, and that last word, it rhymes with stitch, but yeah. So this was one girl who definitely made the room unstable. Now, I wish I could say on that particular day that was the only kid that I had to ask to leave. There was 2 more. It was a rough day. Every time one of those less than well-behaved individuals, I am recording this, so I have to say it kind of nicely. Every time they left, the room got a little bit better. I mean, when you have a girl that just decides to swear every other word and they leave and they're in the middle of play fight, things get better. And then another one leaves, another one. Things slowly get better. Now, as a teacher, no longer is all my energy having to be used to, well, here, look what's going on here, what's going on there, trying to get everyone just to not destroy each other. Because remember, we're actually supposed to teach you something too, not just prevent you from harming each other or the building. Every time one of them left, one of them were emitted, things got a little bit easier. And if they got a little bit easier, I can kind of breathe a little bit of sigh of relief. I can let out a little bit of energy that was used to hold them together. And that's basically what's happening when you have an unstable nucleus. It is taking a lot of energy to keep that thing held together. And then all of a sudden, alpha shoots out. A little bit easier now. But sometimes an alpha isn't enough. Now you got to do a little bit more. Maybe a beta gets shot out as well. A little bit easier still. The top 3 on this list are all dealing with particles being emitted from the nucleus. Again, too big, too many neutrons, too many protons. The bottom one is that energy. Since energy traveling in waves, we talked about that with light. Gamma is on the electromagnetic spectrum after all. You have visible light, you have UV, then you have gamma rays later on as well. That energy to hold that nucleus together is what's released. It's what we kind of refer to as that radioactivity.